For most of human history, gravity felt like the one thing we never had to question. It was the quiet pull that kept our feet on the ground, the unseen force that choreographed planets around the sun, the gentle curve that shaped the motion of galaxies across unimaginable distances. Even when Einstein revealed that gravity was not a force at all, but the bending of space-time, this revelation still carried an air of finality. It suggested that we had reached the bedrock of explanation, that beneath the elegance of curved geometry, there was nothing deeper left to uncover. Yet a strange set of discoveries at the edge of astrophysics, quantum theory, and thermodynamics began to suggest a different picture. These clues came not from the familiar world of falling apples or orbiting moons, but from the darkest and most extreme objects in the universe, the ones we used to believe swallowed information with perfect silence. The surprise began with black holes. According to classical general relativity, a black hole has no structure beyond its mass, spin, and charge. Everything else is erased. But in the 1970s, researchers realized that something essential had been overlooked. A black hole behaves like a thermodynamic object, possessing a temperature and an entropy. That entropy is not hidden deep inside, but is instead proportional to the area of its event horizon. If a black hole has entropy, then it must have microscopic degrees of freedom. Something in space-time itself must be storing information. This insight cracked open a door that no one had expected, because entropy is not a geometric quantity. It is a statistical one, a count of how many microscopic states can produce the same outward appearance. What emerged from that realization was a startling possibility. Maybe gravity was not fundamental after all. Maybe gravity was the large-scale echo of countless unseen degrees of freedom, the way temperature is the echo of countless molecular motions. This idea matured through the work of several theorists, but it was a single argument by physicist Ted Jacobson that gave it an unavoidable sharpness. He imagined slicing space-time into tiny local patches, each with its own horizon seen by an accelerating observer. Then, he demanded something simple and almost innocent. He insisted that the usual thermodynamic rule must hold. A small amount of energy passing through the horizon must produce a small change in entropy. Yet when he applied this thermodynamic relation to the fabric of space-time itself, something remarkable happened. Out came Einstein's field equations. In this light, gravity became the thermodynamic behavior of a deeper microscopic structure. If this is correct, then all the elegance of curved space-time is not the first layer of reality, but a consequence of something hidden beneath. Verlinde expanded this idea, describing gravity as an entropic force, the same kind of collective effect that shows up in stretch polymers or in the random motions of molecules drifting from high concentration to low. A mass displaces and disturbs the distribution of microscopic degrees of freedom that encode the information of space-time, and the system responds by drifting towards states of higher entropy. To us, that drift feels like an attractive pull. What we call a gravitational force is simply the universe seeking more possible microstates. The idea is unsettling because it reverses the hierarchy that physics once accepted. We used to believe that matter tells space-time how to curve, and space-time tells matter how to move, and that was the end of the story. But if the curvature itself emerges from entropy, then gravitational attraction is not a primary rule. It is a statistical preference. Gravity becomes a symptom of deeper information, not its master. This does not weaken Einstein's theory, but enriches it. General relativity becomes like thermodynamics. It is accurate, powerful, beautiful, and yet not fundamental. Such a reversal forces a different question. If gravity emerges from entropy, then what creates entropy in the first place? Entropy is not a mystical substance. It reflects the number of ways a system can be arranged without changing how it appears on the surface. But for space-time to curve through entropic principles, something must be supplying the microscopic ingredients whose arrangements we are counting. Something must be generating the information, the correlations, the fluctuations that give rise to entropy. Without that, the entropic picture of gravity loses its foundation. This is where the mystery deepens, because entropy is not simply a measure of disorder, as many popular explanations suggest. It is a measure of possibility. It reflects the number of stories a system can tell about itself at the microscopic level, while still producing the same outward identity. If gravity arises because the universe tends to explore more possibilities, then something must be opening those possibilities. Something must be increasing the number of states the universe can occupy. Something must be driving the growth of information itself. The deeper question becomes unavoidable. What is the true engine of entropy? What principle or condition or cosmic event made it possible for the universe to possess low entropy at the beginning and then evolve into higher entropy over time? This question points beyond gravity, beyond thermodynamics, and into the origin of time's arrow. For gravity to be emergent, entropy must be abundant. For entropy to be abundant, the universe must have started in an extraordinarily special state. Why would it do that? What selected that initial condition? And why does the universe continue to evolve in a direction that favors more possibilities rather than fewer? These questions form the core of this book. The more we learn about gravity, the more it dissolves into information. The more we study entropy, the more it dissolves into quantum entanglement and cosmic expansion. The more we search for the universe's foundations, the more we are pulled toward the idea that the universe is not built from matter or forces, but from relationships, correlations, and the flow of information across time. The idea that gravity might be a statistical outcome rather than a fundamental rule feels strange only because we have grown accustomed to treating the large-scale world as the anchor of reality. We trust what we see. We trust the solidity of matter, the curvature of space-time, the pull we feel when we stand on the surface of the sun-warmed Earth. Yet nature has repeatedly shown that the structures we once believed were foundational often turn out to be emergent. Heat is not a basic property, but the collective agitation of molecules. Pressure is not a basic force, but the average momentum of many particles colliding with a surface. Even the familiar rigidity of solids is not fundamental. It arises from the synchronized behavior of quantum mechanical bonds that hold atoms in place. If these ordinary features of our world are emergent, why not gravity as well? The path that led physicists to this startling conclusion was not built from speculation, but from pressure exerted by facts that refuse to fit the classical picture. One of those facts is the notion that horizons have temperature. A horizon is merely a boundary that separates one observer's visible region from another's. Yet quantum fields do not respect such boundaries quietly. To an accelerating observer, even empty space glows with heat. This phenomenon is called the Unruh effect, and although we have not yet measured it directly, its theoretical foundation is solid. When quantum fields are viewed from different states of motion, their vacuum states do not agree, and what is vacuum to one observer becomes thermal radiation to another. The presence of horizon temperature means that space-time horizons behave thermodynamically. They filter energy, exchange heat, and therefore must be connected to microscopic states. Another clue came from black hole evaporation. Hawking radiation showed that these cosmic giants are not eternal, but slowly release energy in the form of thermal particles. This process cannot be described without invoking entropy and temperature. The horizon of a black hole seems to encode all the information that fell into it, storing it in a way that scales with surface area rather than volume. This peculiar surface behavior echoed an even more general idea, sometimes called the holographic principle, which proposes that the maximum information content of any region of space is proportional not to its volume, but to its boundary. In other words, the universe might behave like a hologram, where the fundamental information lives on lower dimensional surfaces and the familiar three-dimensional world is the emergent projection. It is here that many people misunderstand what physicists are saying. They imagine that gravity being emergent means gravity is an illusion, something unreal or fictitious. But emergent does not mean unreal. Temperature is emergent, but it is measurable. Pressure is emergent, but it can crush steel. Gravity, in this picture, is just as real as any other emergent phenomenon. What changes is our understanding of its origin. Instead of imagining gravity as a primary rule inscribed into the architecture of spacetime, we see it as the macroscopic language spoken by a deeper informational network. To appreciate this shift, imagine holding a book. On the surface, it is a solid object with weight and texture. But at the microscopic level, it is a collection of countless atoms bonded together through electromagnetic forces. The solidity you feel is the statistical accumulation of many tiny interactions. Now imagine space-time itself as a similar structure, smooth on large scales, described by elegant equations, but beneath that smoothness lies a sea of microscopic variables. These variables might be quantum bits of area on a horizon, or entanglement links between regions of space, or something even more elementary that we have not yet conceptualized. Whatever they are, their collective behavior produces the geometry that Einstein described. If this idea does not feel revolutionary enough, consider its implications. When a planet orbits a star, we think of the planet following the straightest possible path through curved spacetime. But if spacetime curvature itself is emergent, then the planet's trajectory is not being dictated by fundamental geometry. It is responding to the statistical tendencies of a deeper microscopic system whose entropy gradients push it along the path we interpret as gravitational. In a sense, gravity becomes a kind of memory. It encodes the way microscopic states reorganize themselves in response to matter and energy. This narrative challenges our intuition, but it is supported by mathematical precision. Jacobson's derivation is not hand-waving philosophy. It starts from accepted quantum field theory, uses the well-established Unruh temperature, and ends with Einstein's field equations. It shows that if spacetime holds entropy proportional to its area, and if energy flow across a horizon obeys the standard thermodynamic relation, then the familiar law of gravity naturally emerges. Under this view, general relativity becomes an equation of state, similar to how the ideal gas law captures the bulk behavior of countless molecules. Once this perspective sinks in, the universe begins to look different. The smooth fabric of spacetime is no longer the fundamental scenery, but the average behavior of hidden degrees of freedom. Black holes no longer seem like singular mysteries, but as thermodynamic objects whose entropy and temperature are clues to the deeper architecture of the cosmos. Even the expansion of the universe invites reinterpretation, since the changing horizon of the observable universe carries its own entropy that evolves with time. All of this forces a profound inversion of the usual question. Instead of asking why gravity exists, we begin to ask what statistical properties must exist so that gravity can arise at all. Instead of asking what curves spacetime, we ask what microscopic structure gives rise to curvature as an emergent description. This shift in thinking is the heart of the Great Reversal. It places entropy in the position formerly held by gravity. Gravity becomes secondary. Entropy becomes primary. But entropy is not a simple character. It measures the number of microscopic states consistent with the world we observe. That means entropy is a measure of possibility. Higher entropy corresponds to more possible microstates. Lower entropy corresponds to fewer. If gravity is driven by entropy, then gravity is driven by the universe's preference for exploring more possibilities. Yet such a preference cannot emerge from nothing. Something must create the microscopic states. Something must set the stage for entropy to grow. Something must determine why the early universe began in a low entropy configuration. These questions shift our attention away from gravity as a geometric phenomenon and toward the origin of information itself. Without information, there is no entropy. Without entropy, there is no emergent gravity. Without emergent gravity, the large-scale structure of the universe would not exist as we know it. Thus, the real mystery, the one lying beneath the Great Reversal, is not why gravity behaves the way it does, but why the universe contains the information it does, and how that information has evolved through time. The more deeply we follow this thread, the more gravity dissolves into something like a shadow cast by processes that are not themselves gravitational. It becomes the visible outcome of invisible bookkeeping. This does not diminish gravity's importance. Instead, it elevates entropy to a role far grander than anyone in the 19th century could have guessed. Entropy, once introduced to describe steam engines and ideal gases, now reaches into the largest structures of the cosmos. It shapes galaxies, stabilizes orbits, and guides the formation of black holes. It whispers through the equations of relativity, hinting that the universe is not built from geometry, but from information arranged so cleverly that geometry is the only language we can see. When we say that gravity might be emergent, we are not saying that space-time is illusory, or that curvature is some kind of holographic trick with no substance. We are instead acknowledging that large-scale order usually arises from deeper rules that are simpler and more abstract. A single water molecule is not wet, but a trillion molecules behave like a fluid. A single grain of sand does not form a dune, but the motion of countless grains interacting through wind and gravity creates smooth, sweeping arcs across deserts. Space-time curvature may be similar. The microscopic entities might not resemble geometry in any way, yet their collective behavior creates a fabric that bends and ripples and holds the weight of stars. One of the most striking hints that geometry arises from information comes from the way quantum entanglement behaves across space-time. Entanglement is a peculiar feature of quantum theory, where the state of one system cannot be fully described without the state of another, even if the two systems are far apart. It is as if the universe weaves threads that stretch across space, tying distant regions together with shared information. These threads are not forces, they carry no energy, yet they define possible correlations between measurements. Some physicists have proposed that these entanglement patterns act like the scaffolding from which space-time emerges. In this view, space is not a container in which particles sit. It is the vast network of relationships between degrees of freedom. Geometry is the way those relationships appear when seen from afar. If this picture is even partly correct, then when a massive object moves, it is not sliding through a static geometric arena. Its motion is altering the entanglement structure of space-time itself, and the universe responds by shifting the effective geometry in a way that we interpret as gravitational attraction. This response is statistical, not mechanical. It comes from the same principle that causes a system to drift towards states with more microstates. Entropy gradients become curvature gradients. Curvature gradients become gravitational forces. The chain of explanation runs downward, always pointing toward information. Yet if the story stops here, the mystery remains unresolved. Emergent gravity tells us how entropy can produce the force we call gravity, but it does not tell us where the entropy itself originates. The black hole entropy formula suggests that space-time has a maximum information density determined by the area of horizons. The Unruh effect suggests that even empty space contains thermal behavior for certain observers. Entanglement suggests that the vacuum is full of unseen correlations. All of these point to microscopic structure, but they do not explain why the universe's initial conditions were so extraordinarily smooth. Physicist Roger Penrose highlighted this puzzle with remarkable clarity. He noted that the early universe must have had extremely low gravitational entropy. Matter was spread almost perfectly evenly, and space-time curvature was nearly uniform. A smooth universe has fewer gravitational degrees of freedom than a clumpy one, because clumps can form stars and galaxies and black holes, each containing vast amounts of entropy. If entropy naturally grows, then the early universe must have started in a state with an astonishingly small number of gravitational microstates. Penrose estimated the probability of such an initial state, if chosen at random, to be unimaginably tiny. It is not just 10 to the power of 67 or even 10 to the power of 100. It is so small that writing it out requires exponent towers stacked upon exponent towers. The early universe was not just special, it was extraordinarily special. Why would the universe begin this way? Why would it start with low gravitational entropy when high entropy states are overwhelmingly more common? This question is not a matter of taste or philosophical preference. It is the reason time has a direction. The growth of entropy is what allows stars to shine, what drives chemical reactions toward completion, what lets galaxies form, what pushes the universe from simplicity to complexity. If the early universe had been high entropy, nothing interesting would have happened. No galaxies, no stars, no planets, no life. The arrow of time would not exist. Every process would be reversible. The cosmos would drift in a static haze of thermal equilibrium. Yet our universe is not static. It evolves. It structures itself. It creates. And its creativity comes from this initial asymmetry. If gravity is emergent from entropy, then entropy is the substrate upon which cosmic evolution draws its strength. But something must explain the origin of that entropy and the reason it grows. Something must explain why the universe began with such a remarkable imbalance between what it was and what it could become. Some propose that cosmic inflation provides the answer. Inflation is a period during which space expanded at an extraordinary rate in the earliest fraction of a second after the Big Bang. This accelerated expansion would have smoothed out any irregularities, leaving space-time in a near-uniform state. Yet even inflation requires its own initial conditions. Something must have triggered it. Something must have set its parameters. Something must have created the quantum fluctuations that seeded the structures we observe in the cosmos today. Inflation may spread smoothness, but it does not fully explain why the seed of smoothness was present to begin with. And so the great reversal brings us to the path this book will follow. By examining gravity as an emergent phenomenon, we are compelled to study entropy with far more seriousness than ever before. We must understand entropy not only as a mathematical quantity, but as the engine of cosmic evolution. We must understand where it comes from, how it behaves, and why it grows. We must explore whether entropy arises from quantum entanglement, from the expansion of space, from the rules of quantum information, or from the very initial act of the universe choosing a particular state from an ocean of possibilities. In this quest, gravity is no longer the starting point. It is the destination. The true origins lie deeper in the nature of information and the strange, subtle processes that allowed the universe to begin in profound simplicity and unfold into profound complexity. When people first hear the word entropy, they often imagine it as disorder, as if the universe began neat and tidy and has been slowly unraveling ever since. This picture is convenient but misleading. It carries the flavor of a moral story, as though the cosmos began with everything in its proper place and now drifts toward chaos out of cosmic laziness. But entropy is not a judgment about messiness. It is not a commentary on beauty or ugliness. It is something far simpler and far more profound. Entropy is a count of possibilities. To understand this, imagine a simple scene. You walk into a library and see a book lying open on a table. At first glance, the situation is perfectly ordinary. But imagine that someone asks a strange question. How many ways could the tiny molecules of the air in the room and the fibers in the book and the atoms in the table be arranged, while still presenting you with this same outward image of a book on a table? The answer is enormous. You are seeing one arrangement out of an astounding number of microscopic possibilities. All of those possibilities belong to the same macrostate. Entropy measures the size of that set. Higher entropy simply means there are more microscopic configurations compatible with what you see. This is the essence of the idea that Ludwig Boltzmann captured more than 100 years ago. On his tombstone in Vienna, a simple formula is engraved. It states that entropy is proportional to the logarithm of the number of microstates that correspond to a given macrostate. Although scientists often express things in compact mathematical form, the meaning is surprisingly intuitive. The more ways a system can be rearranged without changing how it appears macroscopically, the higher its entropy. This idea becomes even clearer when viewed through the lens of information theory. Claude Shannon introduced a concept nearly identical to entropy, but he expressed it as a measure of missing information. If you know exactly what microscopic state a system is in, the entropy is low because you are missing little. If you know only the large-scale features and none of the details, then you are missing a great deal of information. That missing information tallies up to the entropy. In other words, entropy counts how many questions you would need to ask in order to specify the state of a system precisely. Entropy is therefore not about disorder in the common sense. A deck of cards arranged in perfect sequence from ace to king is not low entropy because it looks neat. It is low entropy because there are few microstates that correspond to that specific arrangement. Shuffle the deck thoroughly, and the outward appearance changes little. It still looks like a pile of cards. But the number of possible microscopic arrangements compatible with that shuffled state explodes. The system has more possibilities, and therefore more entropy. If you spilled that deck across a table, the cards might appear messier, yet the entropy might be lower than a well-mixed pile, because the constraints of their positions reduce the number of compatible microstates. This shows why disorder is a misleading metaphor. Entropy cares only about the number of possible configurations, not whether something looks tidy. This shift in understanding transforms every conversation about the universe. When we talk about entropy increasing, we are not talking about the universe becoming chaotic in an everyday sense. We are talking about the universe drifting toward macrostates that can be realized in more microscopic ways. High entropy states dominate not because nature prefers disorder, but because nature has many more ways to produce them. When you consider all possible ways atoms can arrange themselves, the overwhelming majority produce states with high entropy. This fact alone guarantees that entropy tends to rise, not because the universe has a rule commanding it, but because probability overwhelmingly favors it. In this sense, entropy measures the richness of possibility space. When a system evolves, it tends to flow into regions of that space where the landscape offers more routes. It is like a river flowing downhill into a broad valley. The wideness of the valley corresponds to the abundance of microstates. To flow into a narrow valley would require exquisite precision, while flowing into a broad one requires almost none. The wider the valley, the more naturally the system arrives there. Entropy is the measure of that wideness. This interpretation matters enormously for the story of gravity. If gravity truly emerges from entropy, as entropic gravity proposals suggest, then this flow toward wider valleys is not just a feature of gases or card decks. It is a feature of space-time itself. The geometry of the universe bends because the underlying microscopic states of space-time are arranged in such a way that certain configurations have more available microstates than others. Matter curves space-time because its presence changes the landscape of possible microscopic arrangements, and space-time shifts in response to maximize its entropy. This narrative turns gravity into a statistical effect of the same kind that drives diffusion, heat flow, or the distribution of molecules in a closed box. The universe is not falling apart. It is simply exploring more of its possibility space. Yet a deeper question lurks beneath this neat explanation. If entropy measures possibility, where do those possibilities come from? What supplies the microstates? Why does the universe have such an enormous capacity for variation in the first place? It is not enough to say that entropy is high because the universe is large. The early universe was small by present standards, yet possessed conditions that led to an extraordinary growth of entropy over cosmic time. This means something about the initial state allowed this expansion of possibilities. Something about the birth of the cosmos created the potential for entropy to rise. To understand this, we must examine what entropy really means when applied not just to matter, but to space-time. When we say a black hole has entropy, we are counting configurations not of atoms, but of the microscopic constituents of space-time itself. When we say the horizon of the universe carries entropy, we are counting the number of ways quantum fields can arrange themselves while respecting the limits set by the cosmic horizon. These microstates are not visible, yet their existence is forced upon us by the laws of thermodynamics and by the behavior of horizons. Space-time holds information, and that information can be arranged in many ways. Thus, entropy becomes a measure of how many ways reality can be constructed while still yielding the same large-scale world we observe. It becomes the hidden combinatorial foundation upon which physics rests. Every gravitational effect may be tied to shifts in this combinatorial structure. Every bend in a light beam near a star may reflect the statistical push of countless microstates. Every orbit of a planet may be a subtle dance of information rearranging itself beneath the veil of geometry. To say gravity comes from entropy is therefore to say gravity comes from the counting of possibilities. But this raises a question that cannot be avoided. If entropy is the count of possibilities, then what determines the number of possibilities to begin with? Why does a universe exist that can be arranged in so many ways? Why are there microstates at all? Why is there information embedded in space-time? Why does the cosmic fabric have the capacity to store these invisible degrees of freedom? These questions pull us toward a deeper mystery. We cannot resolve gravity's emergent behavior unless we understand the origin of the entropy that fuels it. And entropy itself cannot be understood without examining the nature of information in the universe. The search for the source of entropy therefore becomes a search for the source of information. It leads us into the early universe, into the structure of quantum fluctuations, into the patterns of entanglement that stretch across space-time, and into the very heart of the cosmic beginning. If entropy measures the number of possibilities compatible with what we observe, then the next natural question is why those possibilities evolve the way they do. Every physical process that we associate with irreversibility, such as heat flowing from a hotter object to a cooler one or a drop of ink spreading through water, is ultimately a story about probability. The second law of thermodynamics, often stated as entropy always increases, is not an iron rule imposed by the universe. It is a statistical truth that arises from the sheer number of ways high entropy states can exist compared to low entropy ones. The universe does not command entropy to rise. The universe simply falls into the embrace of the overwhelmingly likely. Imagine a box filled with a mixture of gas molecules. If all the molecules began in one corner of the box, that would be a low entropy state because there are few microstates that correspond to that arrangement. As soon as the molecules begin to move, they bounce and scatter, swiftly spreading through the whole volume. There are countless more microstates in which the gas occupies the entire box than microstates in which it is confined to a tiny fraction of it. The system shifts naturally toward high entropy because high entropy states crowd the landscape of possibility. It is sometimes said that entropy increases because systems want to become more disordered, but this phrasing misleads. Molecules have no intent. They do not desire disorder. They simply follow the laws of motion, and those laws allow them to explore the possibility space available to them. Since most of that space corresponds to high entropy states, the system almost always ends up there. The same idea emerges in a shuffled deck of cards. If you aim for a specific sequence, such as all the hearts in ascending order, there is exactly one arrangement that meets your goal. But if you aim for a random-looking mixture, you have an extraordinary number of arrangements that satisfy that condition. The random pile is not special, it is typical. The ordered stack is rare. This simple truth about probability becomes profound when extended to the entire cosmos. The growth of entropy does not arise from a fundamental time direction encoded in the laws of physics. The microscopic laws, whether classical or quantum, are nearly all reversible. If you filmed a pair of colliding particles and played the tape backward, the motion would look perfectly plausible. Nothing in the equations forbids time reversal. Yet when we observe the macroscopic world, we see a clear arrow of time. Heat flows only one way. Stars shine only one way. Eggs break, but do not reassemble. The universe expands and cools rather than contracting and heating. These large-scale asymmetries are not consequences of the microscopic rules. They are consequences of the universe, beginning in an extraordinarily low entropy state. It is here that the second law takes on its true meaning. It tells us that given a low entropy beginning, the universe will evolve towards states of higher entropy, because those states are overwhelmingly more numerous. The second law is not a law about the future. It is a statement about the past. If the universe had begun in a typical high entropy state, the arrow of time would not exist. But because the universe began in a special low entropy condition, time became directional. Every irreversible process is a memory of that special beginning. Every moment of evolution is tied to that initial imbalance. Consider the night sky. The stars that shine overhead are not eternal. They are engines that convert low entropy fuel into high entropy radiation. They burn hydrogen into helium and release light and heat into space. They operate only because the universe began, with conditions in which such fuel existed in a concentrated low entropy form. If the early universe had been in equilibrium, filled with a uniform bath of thermal radiation and no gradients of temperature or density, stars could never have formed. Without stars, planets would not exist. Without planets, complex chemistry would not unfold. Without chemistry, life could not emerge. In this sense, the second law of thermodynamics is the reason evolution, development, and history are possible. It creates a universe that moves rather than stalls. Yet we must take care not to confuse the reason entropy tends to rise with an explanation of its origin. The growth of entropy is a natural consequence of probability, but probability alone does not explain why the universe began in a state where entropy had room to grow. That special beginning is a boundary condition, not a consequence of the laws of physics. It must be explained, or at least acknowledged, as the wellspring from which all temporal asymmetry flows. If the early universe had not been so uniform and so smooth, its entropy would have been higher, and the second law would not have led to the same unfolding of cosmic structure. This smoothness is not trivial. It is not merely the absence of lumps. It is the absence of gravitational entropy. Gravitational systems behave differently from gases. For a gas, spreading out increases entropy. For gravity, clumping increases entropy. A uniform distribution of matter carries very little gravitational entropy, while a clumped distribution can carry enormous entropy because clumping leads to the formation of black holes, and black holes carry the largest entropy known in physics. Thus, the smooth early universe was not a state of maximal disorder. It was a state of extraordinary order with respect to gravity. This means the second law, in the cosmic sense, has a unique source. It arises not because matter behaves statistically with respect to its microscopic degrees of freedom, but because space-time itself began in a state where the gravitational degrees of freedom were highly constrained. Over time, gravity allowed matter to collapse into stars and galaxies, and eventually black holes. Each collapse increased gravitational entropy. Each structure that formed pushed the universe toward a more probable configuration. Every cluster of galaxies, every supermassive black hole, every swirling spiral arm is part of the universe's journey toward more microstates. This perspective transforms our understanding of cosmic history. The growth of structure is often described as the triumph of gravity, the ability of matter to overcome expansion and pull itself together. But from the viewpoint of entropy, the growth of structure is the triumph of possibility. The early universe was like a tightly coiled spring containing enormous potential for entropy growth. As time passed, this potential unwound itself. The formation of stars was one expression of that unwinding. The slow evaporation of black holes will be another expression billions upon billions of years from now. Entropy is the engine behind the cosmic narrative, And that narrative runs only because the universe began in an astonishingly low entropy configuration. This brings us to the central mystery that pushes the story forward. If gravity emerges from entropy, and if entropy measures the number of microscopic possibilities, and if those possibilities determine the arrow of time, then the true origin of the universe's behavior lies not in its forces, but in its information. Something about the beginning created conditions where entropy could grow. Something about the initial state limited the number of microstates so severely that the universe had an entire future waiting to unfold. The next step in the journey is to understand what that initial low entropy state actually was. The common picture of the Big Bang as a hot, dense explosion tells only part of the story. Heat and density alone do not determine entropy. A system can be extremely hot and still have low entropy if its degrees of freedom are constrained. The early universe was like this. It was hot, dense, and uniform. Squeezed into that uniformity was a remarkable level of order. The question is why? Before we turn to the early universe directly, we must explore a subtle point that often goes unspoken. Entropy does not rise because disorder is inevitable. Entropy rises because the initial state was special. This specialness is not explained by the second law. It is assumed by the second law. It is the starting point of the arrow of time. The question of why that starting point existed is one of the deepest puzzles in all of physics. The strange thing about entropy is that it feels like a feature of the world that should be optional, something that could be different if the universe were arranged differently. Yet when we study it closely, entropy appears in every corner of physics. It shapes the behavior of gases. It guides the motion of stars. It governs the aging of black holes. It gives direction to time. It even intrudes upon the vacuum itself, revealing that what we call empty space is not empty, but alive with quantum fluctuations and entanglement. Entropy is not a footnote. It is a central character in the cosmic story, and understanding what it measures is essential to understanding why the universe evolves at all. To appreciate the depth of this role, imagine a universe where entropy does not exist. Such a universe would have no arrow of time. Processes could run forward or backward with equal ease. Heat would not flow. Stars would not radiate. Black holes would not evaporate. Structures might form and dissolve in perfect reversibility. Life, which depends on gradients of energy and irreversible processes, could never arise. A universe without entropy would be motion without memory. It would be a static theater where nothing truly changes, even if movement occurs. Our universe is not like that. It is full of transitions, histories, and consequences. The presence of entropy is what makes evolution, in every sense of the word, possible. This power arises because entropy counts possibilities, and the universe is built from possibility. Every particle in motion, every wave of light, every fluctuation in a quantum field represents a range of potential microstates. When these microstates outnumber the constraints imposed by large-scale conditions, entropy is high. When constraints dominate, entropy is low. This tension between microstates and constraints defines the behavior of everything from the smallest atom to the largest galactic cluster. Yet possibility alone does not explain why entropy grows. The reason entropy increases is that the landscape of possible configurations is outrageously vast in the high entropy region and minuscule in the low entropy region. If you drop a marble into a narrow well, it may stay trapped, but if the well opens into a wide valley, it will roam freely. The early universe was placed at the top of a narrow well, an unlikely position with almost no room for microstates. As time passed, it rolled into the vast valley of high entropy. That descent is what we call the arrow of time. Still, you might wonder why entropy is so intimately bound to information. Why is missing information the measure of entropy rather than something more tangible? The answer lies in the fact that information itself is physical. It is not an abstract bookkeeping device. When you store information on a memory chip, you change the physical state of the device. When you erase information, you increase entropy, because the act of erasure destroys microstate specificity and replaces it with uncertainty. Nature insists that any manipulation of information has energetic and entropic consequences. This principle, first articulated by Rolf Landauer, reveals that entropy and information are two perspectives on the same phenomenon. When you know more about the microstate of a system, the entropy is lower. When you know less, the entropy is higher. This is why entropy expands as the universe expands. When space grows, quantum fields gain new volume in which to fluctuate. Each new region of space contains quantum degrees of freedom that can exist in many microstates. Even if the average energy density falls during expansion, the number of possible configurations rises. More space means more microstates. More microstates mean more entropy. The universe does not simply get colder and emptier as it expands. It becomes richer in possibility. This idea becomes even more intriguing when we consider horizons. The horizon of the observable universe, like the horizon of a black hole, carries entropy because it marks a limit to what we can know about the microstates beyond it. Every horizon is an information boundary. Beyond that boundary, the microscopic details are hidden from view, not because they do not exist, but because they are causally inaccessible. Ignorance is not metaphorical here, it is literal, and that literal ignorance produces entropy. This reveals a profound truth. Entropy is not just a property of matter, it is a property of knowledge. It is tied to what is accessible, to what can be observed, to what can be known. In this sense, entropy is woven into the structure of the universe, not because the universe is messy, but because the universe limits the information any observer can hold. This will become important later when we explore how entanglement across horizons might generate space-time geometry itself. But returning to the central thread, we now see that entropy measures the number of permissible microstates, and that this count relates directly to our incomplete knowledge of the microscopic world. If gravity emerges from entropy, as suggested by entropic gravity theories, then gravity emerges from information that we cannot directly see, but whose statistical behavior dictates the large-scale curvature of space-time. This is why the question of what entropy measures cannot be separated from the question of what reality is made of at its most fundamental level. Yet even after understanding entropy as a measure of possibility, a riddle remains. Why does the universe have the microstates it does? Why does it have the capacity to store information? Why do horizons possess entropy proportional to their area? Why does quantum mechanics allow entanglement that spreads possibilities across space? The existence of entropy is not explained by these features. These features are part of what entropy is measuring. To understand the origin of entropy, we must trace it back to the beginning of time. As we shall see in the chapters ahead, entropy did not begin high. It began very low. The early universe was uniform in a way that defies natural expectation. It was as if someone had prepared a deck of cards and arranged them into a perfect sequence, then released the deck into motion, allowing it to drift into a shuffled state. The shuffling is inevitable. The initial perfect sequence is not. The second law does not explain the smoothness of the early cosmos. It presupposes it. That smoothness is the foundation of the arrow of time. It is the beginning of the cascade of possibilities that allowed stars to ignite, galaxies to form, and observers to ponder their own origins. Thus, Chapter 2 brings us to a sharpened conclusion. Entropy measures the number of microstates consistent with a system's large-scale appearance. It measures ignorance, possibility, and the sheer breadth of the microscopic landscape. It determines the flow of time by linking the special beginning of the universe to the long unfolding of cosmic history. But understanding entropy as a measure is only the first step. The next question is why it grows, and answering that takes us into the heart of the second law itself. From the moment the universe began its expansion, something subtle but relentless unfolded beneath every physical process. Entropy started to grow. It did not grow because of a commandment written into the laws of physics. nor because matter has a fondness for disorder, nor because time itself demanded a direction. Entropy grew because the universe wandered into states that were overwhelmingly more probable. This quiet statistical tendency is the true engine behind the second law of thermodynamics. It is not a decree, it is a drift. To understand this drift, imagine again a deck of cards spread across a table. If the deck begins in perfect order, that configuration is rare in the overwhelming space of possibilities. Shuffle the cards even a little, and the system leaps into a region with far more possible arrangements. Shuffle again, and it leaps into an even larger region. At each step, the system is not seeking randomness. It is simply moving through its possibility space in a way that is almost impossible to reverse. To reassemble the ordered deck requires an astonishing degree of coordination among all the microscopic motions. Such coordination is not forbidden. It is simply unlikely beyond measure. The universe behaves similarly. The early cosmos was like that ordered deck, placed in a delicate and exquisite configuration with extremely low entropy. As soon as the universe began to evolve, it scattered into a vast and rising sea of possibilities. The second law of thermodynamics captures this movement. It tells us that the number of accessible microstates tends to increase with time. But this law is not a fundamental rule in the sense of gravity or electromagnetism. It is a statistical observation about how systems behave when they start in a special state. Consider a room filled with air. Molecules ricochet unpredictably, and yet the large-scale behavior is deterministic. Pressure equalizes, temperature spreads evenly, entropy rises. But if you could reverse the velocities of every molecule in that room, the system would evolve backward in time. Heat would flow from cooler regions to hotter ones. Gas would gather spontaneously into one corner. Entropy would decrease. This reversed evolution is consistent with the laws of mechanics. The only problem is that arranging such perfect microscopic coordination is nearly impossible. The laws do not forbid it. Probability forbids it. This is the essence of irreversibility. It does not arise from the laws themselves, which are nearly all time symmetric. It arises from the fact that low-entropy states occupy a tiny sliver of possibility space. High-entropy states occupy almost all of it. If you place a system somewhere in that space and let it evolve, it will wander toward the vast region naturally. This wandering is what we call the second law. It is not magic, it is mathematics. Now picture the universe shortly after its birth. The hot plasma of particles was nearly uniform, with density variations, so small that they could be described in simple fractions of a percent. This smoothness is not a high-entropy state. It is low because gravitational entropy is minimized when matter is spread thinly and evenly across space. Over cosmic time, gravity amplified tiny fluctuations, pulling matter into clumps, forming stars, galaxies, clusters, and eventually black holes. These structures carry far more gravitational entropy than the smooth sea from which they emerged. In this sense, the universe did not become more disordered. It became more structured, and that structure increased entropy. This may sound counterintuitive, but it reveals something powerful. Entropy does not always align with our everyday sense of messiness. A star is a masterpiece of structure, yet it increases entropy by radiating energy into space. A galaxy is a cathedral of motion, yet it contains black holes whose entropy dwarfs everything else. Entropy guides the universe towards states that are more probable, not necessarily more chaotic. Probability governs cosmic architecture, and high-entropy states can be full of structure. You can picture the universe's evolution as a descent into a valley that becomes wider and wider with time. At the very beginning, the valley is narrow, almost like a sharp ridge. The slightest movement causes the universe to fall into a broader region. As time progresses, the valley expands into a vast plain with countless accessible configurations. The universe does not need to aim, it simply tumbles. And its tumble is what we perceive as the forward march of time. Yet we must take this understanding one step further. If entropy rises because higher entropy states are more probable, then everything we observe in the universe is the result of this simple statistical truth. The formation of stars is a probability-driven process. The clustering of galaxies is a probability-driven process. Even the cooling of the cosmic microwave background, spreading thin across the widening space, reflects the universe's drift toward higher entropy. This drift is not passive. It creates gradients. It fuels motion. It allows energy to flow from concentrated reservoirs to diffuse backgrounds. Life itself emerges because these gradients exist. Without entropy gradients, chemistry would stall. Without chemistry, biology would fail. Without biology, observers would not ponder the nature of entropy. Thus, the second law is not a cosmic curse. It is a cosmic gift. It creates the conditions for complexity to arise, for information to proliferate, for stars to ignite their nuclear fires, and for planets to grow fertile with possibility. It is the quiet sculptor of time. But if entropy naturally rises, we must ask what constrained it at the beginning. Why did the universe begin in a low entropy state that allowed this long ascent into a higher entropy future? Why was the possibility space so limited at the start? This question lies at the heart of cosmology. It is the bridge that connects microscopic physics with the grand sweep of cosmic history. It is the reason the universe is dynamic rather than static. It is the source of every irreversible event that has ever unfolded. As we move forward, we will explore how this low-entropy beginning shaped the cosmos. We will examine how gravitational entropy differs from thermal entropy and why the early universe was so astonishingly smooth. We will see why this smoothness is not automatically explained by expansion alone, and why deeper principles may have selected that primordial configuration. Most importantly, we will confront the possibility that the universe did not simply inherit its low entropy state, but that something profoundly physical determined it. The rise of entropy across cosmic history is so steady and so universal that it often feels like a fundamental law, but its true origin lies not in the equations of motion, but in the overwhelming imbalance between low entropy beginnings and high entropy futures. This imbalance is the silent architect behind time's arrow, a persistent asymmetry that shapes every process from the cooling of stars to the fading of cosmic light. Yet knowing that entropy rises because high entropy states dominate does not tell us why the universe started so improbably low. To approach that question, we must examine how gravity reshapes our expectations of entropy. In everyday thermodynamics, a system tends to spread out. Heat diffuses, molecules scatter, density gradients flatten. These behaviors increase entropy because a spread-out system corresponds to many possible microstates. Gravity reverses this intuition. Under gravity, matter tends to clump, and this clumping increases entropy because it allows space-time itself to explore a larger number of configurations. The most extreme example of this is the formation of black holes. A black hole has far more entropy than any diffuse cloud of gas of similar mass. When matter collapses under its own gravity, it is not moving toward order or simplicity. It is moving toward a state with vastly more microstates and thus vastly more entropy. This means that the early universe, which was smooth and nearly uniform, was not in a high entropy state. It was in an astonishingly low one. There were virtually no gravitational clumps. There were no black holes. There were no stars or galaxies or planets. Everything was spread evenly, like a perfect cosmic mist. Such a configuration is elegant in its uniformity, but it hides a paradox. From the perspective of gravity, the number of microstates available to a smooth universe is incredibly small. The number of microstates available to a clumpy universe is unimaginably larger. When matter later collapsed into galaxies and stars, the entropy increased dramatically, not decreased. Structure formation was not a violation of the second law. It was the fulfillment of it. This inversion of intuition is crucial. In non-gravitational systems, smoothness corresponds to high entropy and clumpiness to low. But in gravitational systems, clumpiness corresponds to high entropy and smoothness to low. This means the early universe was balanced on the very tip of entropy's narrow ridge. Its uniformity represented a state of extreme informational constraint. The universe could have begun in any number of high entropy configurations, but it did not. It began in one that was exquisitely fine-tuned, one that allowed entropy to grow for billions of years. Why does this matter? Because once we understand that entropy behaves differently under gravity, the true mystery of the second law becomes sharper. It is tempting to believe that the early universe must have been smooth because everything was compressed into a tiny volume. But compression alone does not guarantee smoothness. You can compress a system into a tiny region and still pack it with complexity. You can compress matter into a small sphere and still have enormous gravitational entropy if that sphere has already collapsed into a black hole. What makes the early universe special is not that it was small, but that it was smooth. Imagine two universes. Both begin with the same total mass and energy. One is smooth, the other is already clumpy. The smooth universe has far fewer gravitational microstates, and thus far lower entropy. The clumpy universe has many gravitational microstates, and thus far higher entropy. If both universes begin expanding, the smooth universe will see its entropy increase dramatically as structures form. The clumpy universe will not have much room for entropy to grow. Its arrow of time would be weak or non-existent. The fact that we live in a universe that produces stars, planets, chemistry, and life suggests that we occupy the first scenario, the one where the universe was born smooth and low in entropy. This understanding reshapes our sense of cosmic evolution. The universe is not marching toward disorder. It is moving into deeper complexity because the space of high entropy gravitational states is immense and filled with structure. Entropy guides matter into stars and stars into black holes. It shapes galaxies into spirals and clusters into sprawling cosmic webs. Every massive structure is part of entropy's unfolding tapestry. Yet this still does not answer the central question. Why was the universe smooth at the beginning? Some propose that the Big Bang simply selected a low entropy state and that nothing more needs explaining. But this response feels incomplete. In physics, we rarely accept initial conditions without asking what determines them. If the beginning of the universe were completely random, we would expect it to begin in a high entropy state, not a low one. High entropy states are overwhelmingly more probable. For the universe to begin in a state of extreme smoothness is like tossing a deck of cards into the air and having them land perfectly ordered on the table. It can happen, but why would it? Other explanations turn to cosmic inflation. Inflation proposes that the universe underwent a brief period of exponential expansion in its earliest moments. This expansion would smooth out any irregularities, flatten space-time, and cool the universe into a nearly uniform state. Inflation therefore explains the smoothness of the early universe. But inflation itself requires a specific configuration of fields and energies to begin. In its own way, inflation pushes the question backward rather than answering it. We must still explain why the pre-inflationary universe had conditions that allowed inflation to start. This chain of explanations forces us to confront the possibility that the low entropy start was not an accident. It might be the result of deeper informational principles. Some ideas suggest that the universe began in a state of minimal entanglement or minimal gravitational complexity. Others propose that the laws of physics themselves may favor beginnings with low entropy because only such beginnings enable the unfolding of history and complexity. This is speculative, but not unreasonable. In many physical systems, initial constraints shape all future behavior. The universe may be no different. Yet before we explore these deeper ideas, we must fully understand why entropy increases at all. Entropy grows because the number of possible microstates increases as the universe evolves. This is particularly true under gravity, where clumping dramatically expands the range of possible spacetime configurations. It is also true for quantum fields, whose modes multiply as space expands, producing more ways for the vacuum to fluctuate. The simple expansion of space creates new degrees of freedom, and with them, new microstates. The rise of entropy is built into the architecture of a growing cosmos. We can think of the universe as a grand calculation in which the number of possible outcomes increases with time. As more microstates become available, the system naturally moves into them. This motion is not driven by intention or design. It is driven by probability. The universe does not climb toward high entropy. It falls into it. The descent is inevitable because the valley of high entropy states is unimaginably vast. What makes this descent possible is the special nature of the beginning. Without a low entropy start, the universe would have had nowhere to fall. The arrow of time would not exist. The climb into complexity would not occur. The gentle flow of heat, the collapse of matter, the formation of black holes, the emergence of life, all of these depend on the existence of entropy gradients born from that first moment. We now arrive at the threshold of a deeper inquiry. We understand what entropy measures. We understand why entropy grows, but we do not yet understand why it had room to grow at all. To answer that, we must journey to the primordial universe itself, to the moment when space-time first emerged, smooth and delicate, holding within it the seed of an entire cosmic future. From the perspective of thermodynamics, the universe appears to be engaged in a grand unfolding of possibilities. Everything from the faint whisper of the cosmic microwave background to the blazing core of a star reflects the slow unlocking of microstates that were unavailable in the earliest moments. The smoothness of the beginning created a vast potential difference between what the universe was and what it could become. That potential difference is what we call the arrow of time. Yet if we wish to understand the full meaning of the second law, we must look more closely at what it means for something to be inevitable in a probabilistic sense. The inevitability of entropy increase does not arise from force or compulsion. Instead, it arises from geometry. Not the geometry of space-time, but the geometry of possibility. High entropy states occupy an enormous region of this conceptual landscape. Low entropy states occupy a region so tiny that we might never encounter it by chance. When a system is placed in a low entropy region and left to evolve under time-symmetric laws, it tends to drift into the high entropy region simply because that region is so much larger. It is the same as placing a marble near the top of a mountain. The marble will roll downhill, not because it prefers down to up, but because there are vastly more paths that lead downward than upward. This perspective transforms the second law into a statement about the shape of possibility space. It tells us that the universe's evolution is guided by the vast volume of high entropy configurations in the space of all possible microstates. But this still leaves unanswered the crucial question of why the universe began on the narrow mountain ridge of low entropy. If the second law describes the journey, it does not describe the starting point. To understand the starting point, we must reflect on gravity's role in shaping the cosmic landscape. Gravitational entropy is peculiar because it does not behave like thermal entropy. The presence of gravity rewrites the intuitive connection between spreading and disorder. A gas spreads out to increase thermal entropy, but a gravitational system collapses to increase gravitational entropy. The smooth early universe was one of the lowest entropy configurations possible because gravity had not yet sculpted clumps and structures. This means that the cosmic history we observe, with its galaxies, stars, planets, and black holes, is the story of gravity raising entropy. Every spiral galaxy is a signature of entropy's rise. Every cluster of galaxies, strung along cosmic filaments, is another signature. Every black hole is a towering monument to entropy, containing more microstates than any other object with the same mass. This view leads to a deeper realization. The formation of structure is not merely gravitational collapse. It is the universe unlocking microstates that were unavailable in its smooth beginning. When matter falls into a star-forming cloud, when stars ignite nuclear fusion, when supernovae explode, and when black holes grow in the centers of galaxies, the universe is climbing into regions of higher entropy. Structures may appear orderly to the eye, but they represent a release of gravitational potential into new microstates. The complexity we observe is not an exception to the second law. It is its most spectacular expression. Yet even with this understanding, we still face the central enigma. Why did the universe begin in a state so smooth that gravitational entropy had room to explode across billions of years? Physicist Roger Penrose famously argued that this low entropy state was so improbable that it required explanation. The number of possible gravitational configurations that correspond to a universe as smooth as the early cosmos is extraordinarily small. Penrose calculated that the probability of this occurring by chance was not merely tiny. It was unimaginably minuscule, a fraction so small that writing it out would take far longer than the age of the universe. This suggests that the low entropy beginning was not a lucky accident. Something selected it. Some scientists argue that cosmic inflation explains the smoothness. Inflation stretches space so rapidly that irregularities are ironed out. Small quantum fluctuations are magnified into the seeds of galaxies, but overall, inflation creates uniformity. Yet inflation itself must begin in a low entropy state to operate. A universe already in a high entropy gravitational state would not inflate. This suggests that inflation is part of the story, but not the origin of the story. It is a mechanism that preserves and amplifies an already smooth configuration. It does not create that configuration from scratch. Others turn to quantum cosmology, proposing that the initial state of the universe might have been determined by a quantum rule, perhaps one that minimizes gravitational degrees of freedom, or one that emerges from a deeper principle of information. According to this view, the early universe did not stumble accidentally into smoothness. It arose from a fundamental constraint on the structure of reality. The beginning might reflect a boundary condition built into the laws themselves, or it might represent a selection principle that favors states capable of producing observers, or complexity, or stability. These ideas remain speculative, but they share a common theme. They suggest that the low entropy beginning was not arbitrary. To appreciate the weight of this mystery, imagine that you walk into a vast room full of sand. The sand is arranged into a perfect mural depicting a landscape. The image is delicate, detailed, and extraordinarily precise. Your first instinct would not be to assume that the pattern appeared by accident. You would ask what forces created it, what rules shaped it, what hands designed it. The early universe is like that mural. It is too smooth, too uniform, too special to ignore. Something must explain why it began this way. This does not imply design in any anthropomorphic sense. Instead, it implies that the laws of physics may be deeper than we currently understand. Perhaps the initial conditions of the universe are not free parameters, but consequences of deeper informational rules. Perhaps reality is constrained in a way that forces the universe to begin in a low entropy state. Or perhaps the space of initial conditions is structured in such a way that the low entropy beginning is natural from the perspective of a more fundamental theory. These possibilities remain open. What we do know is that the second law depends on this beginning. Without the low entropy start, entropy would not rise, the arrow of time would not exist, and the universe would not evolve into complexity. Every motion we observe, every star that shines, every heartbeat, every chemical reaction, every thought, all of these depend on the fact that the universe started in a state with room for entropy to grow. Thus, Chapter 3 brings us to a sharpened realization. The second law of thermodynamics is not a law about disorder or decay. It is a law about probability flowing from a special beginning. It is a law about the unlocking of microstates that were inaccessible at the start. It is a law about the unfolding of potential inherent in the smoothness of the early cosmos. Understanding this prepares us for the next step. We must now turn to the low-entropy beginning itself, the moment in which the universe set its arrow of time and opened the door to billions of years of evolution. When we look back toward the earliest moments of the universe, we often imagine a chaotic and violent beginning, a turbulent explosion of energy and matter. The usual picture is one of heat and density so extreme that ordinary physics bends under the weight of it. Yet the deeper we study the early cosmos, the more this popular image dissolves. Far from chaos, the early universe was astonishingly smooth, balanced, and uniform. This smoothness is not a cosmetic detail. It is the central fact behind the arrow of time. It is the foundation upon which all later complexity is built. To appreciate this, imagine the universe when it was only a few 100,000 years old, long before stars or galaxies existed. Matter was spread nearly evenly across space, with only the tiniest ripples in density. These ripples were so small that their amplitudes could be described as fractions of 100,000. They are preserved today in the faint glow of the cosmic microwave background, which shows temperature variations so slight that they resemble the imperfections in a polished gem. This near-perfect uniformity is the reason the universe appears the same in every direction, and why early cosmology can be described with equations of remarkable simplicity. But hidden inside this simplicity is one of the greatest mysteries in physics. The early universe was not only uniform, but low in entropy. This is surprising because the universe was extremely hot. Heat usually corresponds to disorder, and disorder usually corresponds to high entropy. But heat is not the correct measure here. Entropy does not measure how hot something is. It measures the number of microscopic configurations available to a system, and the number of gravitational configurations available to a smooth universe is extraordinarily small. The slightest clumping of matter increases the number of possible microstates. The formation of stars increases it even more. The formation of black holes increases it beyond anything else we know. Thus, the early universe was not bursting with disorder. It was poised in an exquisitely ordered state. This fact was made precise by Roger Penrose through the idea that gravitational entropy is tied to the curvature of space-time. The smooth early cosmos had extremely low Weyl curvature, which is a measure of the free gravitational field. The curvature that existed then was the Ricci curvature produced by matter, but the free gravitational field, the part that describes tidal distortions and gravitational waves, was nearly zero. Penrose argued that this low Weyl curvature reflects an extraordinarily low gravitational entropy. He offered what he called the Weyl curvature hypothesis, the proposal that the Big Bang was not a random high entropy event, but a special boundary condition with vanishing gravitational degrees of freedom. In simpler terms, the early universe was not allowed to explore the huge space of gravitational microstates. It was trapped in a tiny corner of possibility space. This raises a profound question. Why would the universe begin in such a special state? Why would it start with its gravitational degrees of freedom so tightly restricted? There are countless more ways for matter to be arranged unevenly than evenly. There are countless more ways for curvature to vary than to be nearly zero everywhere. If the initial conditions of the universe were selected randomly from the space of all possibilities, the chance of obtaining a smooth universe would be unimaginably small. Penrose estimated that the probability was something like 1 part in 10 to the power of 10 to the power of 68. To write that number out would require more digits than there are particles in the observable universe. It is not merely unlikely, it is so improbable that the universe could never come close to such a state by accident. This insight may seem abstract, but its consequences ripple across all of physics. Without the low-entropy beginning, there would be no arrow of time. All irreversible processes, from the cooling of a hot cup of tea to the evolution of galaxies, depend on the universe having begun in a condition far from equilibrium. The growth of density fluctuations, the formation of stars, the ignition of nuclear fusion, the collapse of massive objects into black holes, all of these events increase entropy. but they can only increase entropy if there is room to grow. The early universe provided that room. The curiosity of this situation deepens when we consider that the early cosmos was hot, dense, and filled with interacting particles. One might assume that such a state would be high entropy, but heat and density alone do not determine entropy. A high-temperature system can have low entropy if its degrees of freedom are constrained. This is exactly what happened in the early universe. The matter content was extremely energetic, but the gravitational field that surrounds and shapes matter had almost no freedom to vary. Its microstates were compressed into a tiny subspace of what should have been possible. This constraint is what allowed the later growth of stars and galaxies to raise gravitational entropy so dramatically. Another way to see this is to imagine a uniform cloud of gas hanging in space. Without gravity, the gas spreads out and becomes more diffuse over time, increasing thermal entropy. But with gravity active, the gas collapses into a star, increasing gravitational entropy. The collapse releases heat, drives nuclear reactions, and ultimately forms a structure with more available microstates. The direction of entropy change depends on which degrees of freedom dominate. In the early universe, gravitational degrees of freedom were dormant. When they awakened through the growth of perturbations, the entire cosmic structure formation process became an expression of the second law. This interplay between smoothness and entropy raises a question that cuts to the heart of cosmology. What set the universe's initial gravitational degrees of freedom to zero? Was this a physical law, a boundary condition, or something deeper? Did the Big Bang enforce smoothness through principles we do not yet understand? Or was the smoothness itself a clue that space-time and gravity are emergent phenomena whose microscopic origins naturally restrict early configurations? Some proposals suggest that quantum gravity may dictate a unique initial state. Others suggest that the geometry of space-time near the beginning was so constrained by quantum fluctuations that only smooth configurations were stable. Still others propose that the laws of entropy themselves might not be meaningful before a certain moment, and that the early universe simply emerged in the lowest available entropy state because no other possibilities were physically allowed. These ideas remain open and debated, but they share a common message. The low-entropy beginning was not trivial. It is also important to recognize that the early universe was not perfectly smooth. The tiny ripples in density, which we now observe as temperature variations in the cosmic microwave background, became incredibly important billions of years later. They served as seeds for gravitational collapse. Regions with slightly more matter pulled in additional material, forming galaxies and clusters. Regions with slightly less matter became the cosmic voids we observe today. These tiny imperfections were quantum in origin. Fluctuations stretched across cosmic scales. Yet even these fluctuations existed against a backdrop of astonishing uniformity. The fact that such faint ripples could shape the entire universe demonstrates how delicately tuned the early cosmos was. If the fluctuations had been slightly larger, the universe would have collapsed into black holes before stars could form. If they had been smaller, matter would never have clumped at all, leaving a nearly empty universe with no structure. The early cosmos balanced on a knife edge, its smoothness punctuated by minute variations that were just right for forming a universe like ours. All of this brings us back to the central meaning of the low-entropy beginning. The universe did not start as a chaotic explosion. It began in a state of profound regularity. Everything that followed, every flash of starlight, every galaxy that swirled itself into elegant arms, every planet that cooled into a home for chemistry, every life form that emerged and wondered about the cosmos, all of it reflects the release of gravitational degrees of freedom that were locked away at the beginning. The universe began smooth so that it could become interesting. It began ordered so that entropy could rise. It began with limited possibilities so that new possibilities could unfold. The low-entropy beginning is not just a cosmological detail. It is the origin of time itself, the reason anything evolves, the reason anything changes, the reason the universe has a story. The smoothness of the early universe is one of the great clues in cosmology. But the universe did not simply appear smooth and uniform by coincidence. Something happened in the first fraction of a second that stretched space-time to an extraordinary degree. That event is known as inflation. It is not simply an expansion, it is an explosive stretching of the fabric of space-time that took a tiny region and magnified it to a size far larger than the observable universe. By doing so, inflation created the conditions from which the arrow of time could emerge. It reset entropy in a very specific way, smoothing space-time and preparing it for the unfolding of structure. Inflation is often described in equations, but its essence can be understood in simple terms. It took the universe from whatever initial irregularities it may have possessed and ironed them almost perfectly flat. To understand inflation, imagine space-time as a flexible sheet. In a normal expansion, the sheet is stretched gently, but in inflation, the sheet is pulled so rapidly and so forcefully that any bumps or curves become nearly imperceptible. This rapid stretching is driven by a field sometimes called the inflaton, whose energy density acts like a form of negative pressure. Negative pressure may sound exotic, but it behaves in a straightforward way in general relativity. It causes space-time to expand faster instead of slowing down. During inflation, this negative pressure dominated the energy content of the cosmos, overwhelming all other influences and driving expansion at an almost unimaginable rate. The stretching was so immense that distances grew by factors written not in tens or hundreds, but in exponent after exponent. This stretching explains one of the most mysterious features of the early universe. Why does the universe look the same in all directions? Regions of the sky that appear similar today were never close enough to interact before inflation. Without inflation, there is no way for them to have equilibrated their temperature or smoothed their density. But if those regions were once tiny and close together before inflation magnified them, then their similarity is no surprise. It reflects a shared past that inflation later stretched across cosmic scales. Inflation did not create smoothness out of chaos. It enlarged a small smooth patch into the vast cosmos we now observe. This picture carries a profound connection to entropy. When inflation stretches space-time, it dilutes any existing irregularities. It washes out curvature, density variations, and gravitational waves. In doing so, it reduces gravitational entropy. It does not eliminate microstates entirely, but it restricts space-time to a narrower range of possibilities. After inflation ends, the universe reheats as energy in the inflaton field converts into particles. These particles fill space with a hot, dense plasma. But unlike the pre-inflationary universe, this reheated state emerges from an enormously smooth geometry. It is a high-temperature state with low gravitational entropy. This combination is unusual. It means the thermal entropy is high because the universe is hot, but the gravitational entropy is low because space-time is flat. This mixture sets the stage for the arrow of time. As the universe expands and cools, gravitational instability begins to amplify the tiny fluctuations left over from inflation. Those fluctuations were once quantum in origin. When inflation magnified them, they froze into classical imprints on space-time. These imprints are visible today as the faint mottling in the cosmic microwave background. They are the seeds from which galaxies grew. Without inflation, these fluctuations would have remained microscopic quantum events. With inflation, they became the blueprint of cosmic structure. The remarkable thing about these fluctuations is that they carry entropy of their own. They represent ways in which the early universe could deviate slightly from perfect smoothness without violating the overall low entropy condition. Inflation created a situation in which space-time was nearly uniform, but not perfectly so. The imperfections were tiny, carefully scaled, and statistically distributed. They provided the universe with the perfect platform for entropy to rise through gravitational collapse. Too much variation, and the universe would have collapsed immediately. Too little, and no structures would have formed at all. Inflation set the variations at just the right level. To picture this, imagine a perfectly calm lake. If it remains perfectly smooth, it reflects the sky, but nothing new happens. If it becomes violently turbulent, waves crash and break without stable forms. But if it carries gentle ripples, those ripples can grow into patterns, reflections, currents, and interactions that create structure. Inflation left space-time with gentle ripples rather than violent ones. These ripples became amplified over billions of years by gravity, shaping the cosmic web of galaxies and voids that fill the universe today. There is also something essential to understand about inflation and entropy. Inflation does not eliminate entropy. Instead, it redistributes it. It pushes entropy outward beyond our observable horizon. Imagine a room crowded with people. If the walls suddenly expand faster than anyone can move, the crowd spreads thin. The density drops. The system becomes more uniform. But the people have not been erased. They have simply been pushed apart so far that their interactions become negligible. Inflation does something similar with space-time. It expands regions so quickly that variations are stretched beyond the reach of causal contact. From the perspective of any one region, entropy appears to have been reduced because most of the microstates have been pushed beyond visibility. This perspective hints at something important. Inflation may solve the smoothness problem, but it does not explain why inflation happened. The inflaton field must have been in a special configuration for inflation to begin. The potential energy of that field must have been high and nearly constant over a region large enough to drive exponential expansion. This requirement itself represents a form of low entropy. In other words, inflation explains the smoothness of the universe, but does not erase the deeper question of why the universe began in a state that allowed inflation to occur. It shifts the mystery one step earlier, but does not eliminate it. Nevertheless, inflation provides the bridge between the low-entropy beginning and the universe as we know it. It takes the early simplicity and amplifies it into a cosmic canvas. It creates the delicate imperfections that later grow into complexity. It gives the universe the room it needs to explore more possibilities, allowing entropy to rise across billions of years. Without inflation, the universe would not have the arrow of time we observe. It would not have galaxies or stars or planets. It would not have structure robust enough to host life. Inflation does not create complexity directly. It creates the conditions under which complexity can emerge. As we look closer, inflation also reveals something subtle about entropy and information. When inflation stretches quantum fluctuations into classical ones, it transforms microscopic information into macroscopic structure. The random variations of quantum fields become imprinted across cosmic distances. This process effectively turns quantum uncertainty into cosmic architecture. It is a conversion of microscopic possibilities into macroscopic ones. In this sense, inflation is not just a geometric event, it is an information-producing event. It increases the number of possible histories the universe can follow. It populates the cosmic canvas with variations that gravity can later amplify. Yet even this does not answer the central question of this book. Inflation shows how entropy was reset and how the arrow of time was set in motion. But what created the fluctuations that inflation stretched? What created the energy of the inflaton field? What created the informational structure upon which inflation acted? These questions push us deeper into quantum theory, into the nature of vacuum fluctuations, and into the possibility that space-time itself contains entanglement at its core. Inflation prepares the stage, but the actors that populate the stage come from quantum processes that lie beneath the surface of classical space-time. To understand where entropy truly begins, we must follow the path into the quantum vacuum itself, into the restless sea of fluctuations that fill even the emptiest regions of space. These fluctuations are not optional, they are required by the uncertainty built into quantum theory. And it is from this restless sea that entropy may have first emerged, long before galaxies spiraled into form, and long before stars lit the darkness. The universe was filled with something that does not resemble matter or energy in any classical sense. It was filled with the quantum vacuum, a restless sea of fluctuations that emerge not from particles, but from the very structure of quantum theory itself. These fluctuations are not optional additions to reality. They are required. Even the quietest possible state of a quantum field carries jitter, uncertainty, and motion. And from this ceaseless activity comes a surprising truth. Even nothing contains entropy. To understand why, imagine that you look at a region of empty space. You might think that nothing is happening there, that all fields are in their lowest energy state. But quantum theory insists on uncertainty. A field cannot have both precisely zero energy and precisely zero variation. If it did, its energy and configuration would be simultaneously known, which violates the uncertainty principle. Instead, the vacuum is a constant churn of momentary particle and antiparticle pairs that flash into existence and vanish again. These are not particles in the classical sense. They are fluctuations in the underlying fields, coming and going in ways that no observer can predict. These fluctuations carry energy, but more importantly, they carry information. The vacuum is not a blank canvas. It is a complex tapestry of correlations. Even in the absence of matter, different regions of space are entangled with one another. This entanglement means that the quantum state of one region cannot be fully described without referencing another. If you divide space into two parts and ask how much information is shared between them, you obtain a measure known as entanglement entropy. This entropy exists even when both regions are in their simplest possible quantum states. The vacuum is not empty. It is full of hidden structure. This structure becomes especially important when horizons enter the picture. A horizon is a boundary beyond which information cannot pass. Black holes have horizons. Accelerating observers have horizons. The expanding universe itself has a horizon that marks the limit of what we can observe. When quantum fields are divided by such a boundary, the entanglement between the inside and outside contributes to an entropy proportional to the horizon's area. This area law is one of the most astonishing features of modern physics. It suggests that the information content of a region of space is not proportional to its volume, but to the area of the surface surrounding it. In this sense, the universe behaves like a hologram, where the fundamental degrees of freedom that encode physical reality may live on surfaces rather than in volumes. This entanglement entropy is not superficial. It affects the dynamics of space-time. Ted Jacobson's insight, which showed that Einstein's field equations can emerge from thermodynamic relations, relies on the idea that changes in horizon area correspond to changes in entropy. When energy crosses a horizon, the entanglement structure shifts, altering the entropy and producing what we perceive as gravitational curvature. Gravity, in this picture, is a response to how quantum information is arranged. It is the macroscopic signature of microscopic entanglement. So where does entropy come from? One answer is that entropy is born from quantum entanglement itself. Every time space is divided, every time a horizon forms, every time a region becomes inaccessible, entanglement produces missing information. That missing information becomes entropy. Even the small quantum fluctuations that inflation magnified into cosmic structure carry entropy because they introduce variation and correlation across regions of the universe. These fluctuations are not random noise. They are part of the quantum foundation from which macroscopic complexity emerges. When inflation stretched these fluctuations across vast scales, it did more than create tiny density ripples. It amplified the entanglement that had been present in the vacuum. Regions that were once intimately connected by quantum correlations became separated beyond the reach of light. The entanglement remained, but the observers living in any one region could no longer access the full quantum state. That inaccessibility creates entropy. Inflation did not simply smooth the universe. It sliced the vacuum into causally disconnected patches, each carrying echoes of the same primordial quantum correlations. This process is deeply informational. It converts the quantum vacuum's internal structure into classical seeds for the universe's future. But the quantum vacuum does something even more important. It fills the universe with possibilities. Every fluctuation represents a microscopic branching of what could occur. When inflation magnified these fluctuations, it scattered possibilities across space. Later, as gravity amplified density variations, some regions collapsed into stars, others into galaxies, others into vast cosmic voids. All of these outcomes can be traced back to the quantum fluctuations that inflation stretched from microscopic to macroscopic scales. The universe did not begin with structure, it began with potential for structure. Quantum fluctuations provided the ingredients, inflation provided the amplification. This raises an important idea. Entropy may have emerged not simply from matter interacting or from space-time curving, but from the quantum fields of the vacuum themselves. Before any particle existed, the vacuum already contained entanglement entropy. When space-time expanded, the number of quantum modes grew. Each mode represents a degree of freedom that can fluctuate in countless ways. As the universe grew, the available space for fluctuations increased. More modes meant more possible microstates. More microstates meant more entropy. In this sense, entropy grows naturally with the expansion of space because space itself creates more room for quantum possibilities. This can be understood through a simple analogy. Imagine a piano with 10 keys. You can play many melodies, but they are limited. Now imagine a piano with 100 keys. The number of possible melodies grows enormously, even if no new rules of music have been added. As the universe expands, it adds keys to the cosmic piano. The quantum fields can occupy more modes, produce more fluctuations, and create more possibilities. Entropy reflects this growth of possibility, yet quantum fluctuations also have something astonishing hidden within them. They suggest that entropy is not a secondary concept, but something that may be woven into the very definition of a quantum field. Because of uncertainty, because of entanglement, because of the impossibility of isolating one region entirely from another, entropy appears even when matter is absent. This tells us that entropy is not merely the result of matter becoming disordered. It is a measure of the quantum fabric of reality. It emerges from the structure of information that exists in even the simplest vacuum state. In this picture, the universe did not begin with nothing and later acquire entropy. The universe began with quantum entanglement and later amplified it. The vacuum fluctuations that inflation stretched were not accidental. They were part of the universe's natural quantum architecture. When inflation magnified them, they became the seeds from which gravitational entropy would grow. The smooth early universe still carried quantum entanglement, and that entanglement held the potential for vastly more entropy than the classical gravitational field could initially express. Even today, much of the entropy in the universe resides not in matter, but in horizons. Black holes hold the largest known entropies. The cosmic horizon itself holds an enormous entanglement entropy. Most of the entropy of the universe lies not in chaos or disorder, but in information that we cannot access because it lies beyond a boundary of knowledge. Entropy is not simply a physical quantity, it is a measure of what can and cannot be known. Quantum fluctuations therefore give us the first clear hint of where entropy originates. It does not arise from matter falling apart or from energy dissipating. It arises from information that becomes inaccessible. It arises from entanglement across boundaries. It arises from the quantum structure of the vacuum itself. When the universe was born, it inherited this quantum structure. When it expanded, it turned potential entropy into actual entropy. When gravity acted on the amplified fluctuations, it drew that entropy into the formation of stars and galaxies. The next chapter will push this further. If quantum fluctuations provide the raw material for entropy, then quantum entanglement may provide the geometry of space-time itself. Entanglement does not simply create entropy. It may be the scaffolding from which space emerges. If the quantum vacuum provides the restless fluctuations from which entropy can arise, then entanglement provides the deeper glue that holds those fluctuations together. Entanglement is one of the most mysterious and essential features of quantum theory. It tells us that two systems can be linked in such a way that neither can be described on its own. This link is not a force, not a signal, not a thread that travels through space. It is a shared quantum state that defies classical intuition. When two regions of space are entangled, they hold information jointly, not separately. And because entropy measures missing information, entanglement naturally becomes a source of entropy whenever part of the system becomes inaccessible. To understand why entanglement is so central, imagine dividing the universe into two regions, region A and region B. If the two regions are not entangled, then the state of region A is independent of region B. But if they are entangled, knowing everything about region A still tells you nothing about region A alone. Instead, it tells you something about the relationship between them. You lose access to the full quantum information unless you can observe both regions together. This lost access becomes entropy. Even if the full universe is in a perfectly pure state with zero entropy, dividing it into subsystems introduces entropy because the correlations between parts become hidden. Entanglement is therefore a natural engine for entropy, one that does not require disorder in the classical sense. It requires only quantum structure. This insight leads to something even more profound. Space-time itself may emerge from entanglement. In recent decades, research into quantum gravity, inspired partly by the idea of holography, revealed that the geometry of space in certain theories is encoded in patterns of entanglement. When entanglement between two regions of a system is strong, the geometric distance between those regions becomes small. When entanglement weakens, the geometric distance increases. In this picture, geometry is not a background stage upon which physics unfolds. Geometry is the manifestation of quantum information arranged in specific patterns. One useful way to picture this is through tensor networks, mathematical structures that represent quantum systems by connecting smaller units of information together. If you arrange a tensor network so that each connection represents entanglement between two quantum units, the overall pattern of connections resembles a discretized space. The network has something like a dimension, something like a curvature, something like a surface. If you increase entanglement, the network tightens. If you reduce entanglement, it stretches. Entanglement plays the role of gravitational field. It determines what counts as near or far. It determines how the shape of the network bends as information flows across it. This idea is made even more striking by the geometric interpretation of entanglement entropy itself. In holographic theories, the entropy of a subsystem is given by the area of a minimal surface that cuts through the geometry. This echoes the entropy of black holes, which is proportional to the area of their horizons. The surface that measures entropy in the holographic picture is not a boundary of matter. It is a boundary of information. This reinforces the idea that space is stitched together by entanglement. If you remove the entanglement, the stitching vanishes. The space collapses into isolated pieces. If entanglement builds space-time, then gravity may be a collective response of that entanglement structure. When the pattern of entanglement changes, the emergent geometry changes. When matter enters a region, it alters the underlying quantum state, shifting the entanglement profile and causing the geometry to curve. From this perspective, gravity is a macro-scale reaction to micro-scale information. It is not a force in the traditional sense, but the way a woven tapestry responds when one thread is pulled. The fabric tightens or loosens depending on how information is arranged. This brings us back to entropy. If entanglement creates geometry, then entropy measures the degree to which regions of space share quantum information. High entanglement corresponds to many quantum correlations. Low entanglement corresponds to fewer. When a region becomes isolated by a horizon, the entanglement across that horizon produces entropy proportional to its area. The more entanglement that is hidden, the more entropy appears. This simple rule holds for black holes, cosmic horizons, and even the vacuum itself. But the story goes deeper. Entanglement does not only create entropy when a horizon forms. It also creates entropy whenever part of a system is traced out or lost to observation. This is why quantum fluctuations contribute to entropy, because fluctuations in one region are entangled with fluctuations elsewhere. If inflation stretches these regions apart, observers lose access to the correlations, creating entropy. If black holes capture information, the horizon hides the entanglement, creating entropy. If space-time expands, the horizon moves outward, changing the entanglement structure and therefore the entropy. These effects combine into a powerful perspective. Entropy is not simply a measure of disorder, it is a measure of entanglement. It reflects the quantum structure of reality. When entropy increases, it often means that entanglement is being spread across larger regions or being hidden behind horizons. When entropy decreases, which is allowed only in extremely special cases, it means that entanglement is becoming more accessible. Consider the formation of a star. On the surface, this seems like an example of decreasing disorder. A star is a structured, well-ordered object. But at the quantum level, the collapse of a gas cloud into a star increases entanglement between the particles and increases gravitational entropy because it allows the gravitational field to explore more microstates. The internal interactions of the plasma create correlations that did not exist before. And the nuclear reactions that ignite the star produce heat and radiation that carry entropy outward. A star burns because entropy increases. Its light is the visible sign of quantum and gravitational entanglement being reshaped across time. Even more striking are black holes. When a massive star collapses under its own gravity, it forms a horizon that hides all the information inside. The entanglement between the interior and exterior of the horizon produces enormous entropy. This entropy is not due to chaos or temperature, though black holes do have temperature. It is due to the loss of information behind the horizon. A black hole is not simply a dense object. It is a boundary of entanglement. Its entropy measures how much quantum information the horizon hides. This helps explain why black hole entropy scales with area rather than volume. The horizon is the dividing line between accessible and inaccessible information. The more horizon there is, the more entanglement becomes hidden. The entropy does not depend on how much matter is inside the hole, but on how much horizon area encloses it. This is one of the deepest hints we have that the universe is a holographic system. If entanglement is the source of entropy, and entropy is the engine behind emergent gravity, then the deepest layer of explanation lies not in geometry or forces, but in information itself. What we call space-time is the macroscopic expression of quantum correlations. What we call gravity is the statistical behavior of entanglement patterns striving toward equilibrium. What we call entropy is the measure of how much of this information becomes inaccessible over time. This perspective also clarifies why entropy increases. As the universe expands, more quantum modes appear. These modes become entangled. Some of this entanglement becomes inaccessible due to cosmic horizons. Some becomes amplified into classical structure. Some becomes buried inside black holes. All of these processes increase the amount of entanglement that is hidden from any local observer. Entropy grows because information becomes distributed more widely and becomes harder to access. Thus, entanglement links the deepest questions of cosmology to the fundamental laws of quantum theory. It shows us that the universe is not built from particles alone, nor from geometry alone, but from relationships. It evolves because these relationships change. It curves because these relationships rearrange. It ages because these relationships become inaccessible. Entanglement is the invisible architecture behind everything. In the next chapter, we will explore how the expansion of the universe increases the number of quantum modes, allowing still more entanglement and therefore more entropy. If entanglement is the source of entropy, then cosmic expansion is the engine that multiplies the possibilities. It adds new degrees of freedom, new places for information to reside, and new paths for the universe to explore. If entanglement provides the scaffolding of space-time and the source of entropy, then the next question becomes how the universe continues to generate the information that feeds this entanglement. The answer lies in the expansion of space itself. As the universe grows, it does not simply stretch existing structures. It creates new room for quantum fields to fluctuate, new modes to exist, and new possibilities to unfold. Information is not conserved in the same way that mass or charge is conserved. Instead, the expansion of space-time increases the number of degrees of freedom available to the universe. With each moment of cosmic time, the universe contains more possible microstates than it did before. This is one of the most extraordinary features of cosmology. Creation does not come only from matter-forming stars or galaxies collapsing. Creation comes from space itself growing. Expansion is an engine that manufactures possibility. To understand how this works, imagine a musical instrument. A violin with a short string can vibrate only in certain ways. Lengthen the string, and more vibrational modes become available. Likewise, when space-time expands, the quantum fields that fill it gain new available wavelengths. The number of allowed quantum modes increases. Each mode is a degree of freedom that can store information, become entangled, or fluctuate. The expansion of the universe does not simply dilute energy, it multiplies the universe's informational capacity. This is why entropy can continue to grow indefinitely. The space of possibilities is not fixed. It expands with the cosmos. This is visible in the behavior of quantum fluctuations that inflation magnified. Before expansion, the fluctuations had only microscopic modes available. When inflation stretched the universe, it created room for those modes to separate and express themselves as classical variations. Later, as the universe continued to expand more gently, even larger wavelengths became relevant. The cosmic microwave background still carries the imprint of these long wavelength modes. The observed temperature variations across the sky are not random noise. They are a fossil record of the early universe's informational growth. As space-time expanded, more patterns became possible. The universe recorded those patterns in the sky, like ink, drying on an ancient scroll. The expansion of the universe also increases entropy through another path. It creates horizons. The faster a region expands, the farther beyond reach certain distant regions become. Light from those regions can never reach us. This creates a cosmic horizon, a boundary beyond which information is lost to observation. When information becomes inaccessible, entropy increases. The horizon hides entanglement. The amount of entanglement hidden behind the horizon grows as the horizon grows. This is why the entropy associated with the cosmic horizon is enormous, far greater than the entropy associated with all the stars and galaxies within it. Most of the entropy of the universe is not in matter. It is in the horizon that surrounds us. It is the measure of how much quantum information lies beyond our reach. Another contribution to the growth of information comes from the formation of structure. When gravity amplifies density fluctuations, it creates a cosmic web of galaxies, clusters, and voids. Each node and filament of this web contains information about the initial conditions, the distribution of matter, and the dynamics of cosmic evolution. These structures are not arbitrary. They hold memory. The collapse of a gas cloud into a star compresses information into nuclear processes. The formation of a black hole preserves information in its horizon area. Even the arrangement of galaxies across billions of light years encodes the history of expansion and the nature of dark matter. Structure formation is an information writing process. The universe is a growing archive of its own past. Black holes are perhaps the most extreme example of informational growth. A black hole's entropy is proportional to the area of its horizon. This means that as black holes grow by swallowing matter, they gain more entropy than any other object could contain. A single supermassive black hole at the center of a large galaxy may contain far more entropy than all the stars in that galaxy combined. Black holes do not merely store information, they dominate it. If the universe lasts long enough, black holes will eventually become the primary repositories of entropy. Their evaporation through Hawking radiation will release that entropy slowly, spreading it across the universe in a thin bath of thermal particles. This is the ultimate expression of cosmological entropy growth. Information created by cosmic expansion, stored through structure formation, and hidden within horizons will eventually disperse across space as the universe fades into cold emptiness. Yet information growth is not limited to the grand scale of galaxies and black holes. Even the presence of particles increases the number of possible microstates the universe can hold. As the universe cooled and matter formed atoms, molecules, and complex structures, the number of possible configurations grew dramatically. Chemistry multiplied the possible arrangements. Biology multiplied them further. The rise of life, thought, and technology expanded the universe's informational landscape in ways not predictable from physics alone. The entropy associated with biological systems is small compared to cosmic entropy, yet the informational richness is vast. Life represents a form of information organization that supplements the physical structures of the cosmos. It emerges from thermodynamic gradients and sustains itself by increasing entropy elsewhere. Life is the universe experimenting with new ways to manage information. But beneath all these processes lies a deeper principle. The universe grows information because it grows space. Expansion increases the number of possible microstates, and entanglement fills those microstates with correlations. Gravity then shapes those correlations into structure. Entropy grows not because systems fall apart, but because the universe continually expands the space of everything that can exist. This is why entropy increases on the largest possible scales. The universe is not a closed box with fixed volume. It is a growing stage. Each moment introduces new possibilities that did not exist before. This growth in possibilities is the essence of entropy. There is another subtle point. Expansion creates room for quantum modes, but it also redshifts energy, lowering the temperature of the cosmic background. This cooling increases the contrast between thermal entropy and gravitational entropy. As matter cools and slows, gravity becomes more effective at drawing it into clumped structures. These structures generate even more gravitational entropy. The interplay between cooling and clumping is essential. The cooler the universe becomes, the easier it is for matter to collapse. The more matter collapses, the more gravitational entropy grows. Cosmic expansion therefore drives entropy in two ways at once. It increases the number of quantum degrees of freedom, and it enhances gravitational processes that raise entropy. The universe is not heading toward equilibrium in a static sense. It is heading toward a state in which the number of microstates becomes so large that the arrow of time will continue indefinitely. Even if all stars burn out, even if black holes evaporate, the cosmic horizon will remain, carrying immense entropy from inaccessible regions. As long as the horizon grows, entropy grows. As long as space expands, possibility expands. The universe favors more because expansion itself creates more. This leads us to an extraordinary conclusion. The growth of information in the universe is not a side effect. It is the central, evolutionary process of the cosmos. Expansion, entanglement, structure formation, and horizon dynamics are all different expressions of the same phenomenon. They all speak to a universe that increases its capacity for information with each passing moment. If gravity is emergent from entropy, then gravity is emergent from this informational growth. If entropy comes from inaccessible correlations, then the growth of entropy reflects the growth of those correlations across expanding space. The deeper we look, the clearer it becomes that the universe is not built from matter alone. It is built from information, constantly rising, constantly diversifying, constantly moving into regions of greater possibility. In the next chapter, we will confront the central divide in cosmology. Does the growth of entropy require explanation through initial conditions, or does it arise from deeper principles that govern information itself? The universe either began with low entropy for a reason, or the laws of information demand that entropy must grow. These two possibilities shape the heart of modern theoretical physics. As we trace the rise of entropy across the history of the cosmos, we repeatedly encounter a fork in the road. One path suggests that everything we observe today, from the arrow of time to the formation of galaxies, arises simply because the universe began in an extraordinarily low entropy state. The other path suggests that the universe behaves this way because deeper informational principles require entropy to grow, principles that may be as fundamental as quantum mechanics itself. The first explanation ties cosmic evolution to an initial condition. The second ties it to a profound law of nature. Determining which of these paths is correct may be the key to understanding why the universe exists in its particular form. To explore this divide, we first consider the initial condition hypothesis. According to this view, the universe began smooth, ordered, and simple. The smoothness was not a consequence of any law. It was just the state the universe happened to occupy at the moment of its birth. Everything that occurred afterward, from inflation to the formation of stars, followed from this special beginning. The second law of thermodynamics, which says entropy increases, would then be a consequence of the universe having started far from equilibrium. No deep informational principle would be needed. The early cosmos was like a ball placed carefully on top of a hill. Once placed there, the ball inevitably rolled downward into states of greater entropy. This picture seems straightforward, but it carries an unsettling implication. Why would the universe begin in such a special state? Low entropy conditions are extremely rare within the space of all possible states. The vast majority of configurations are chaotic, clumpy, and high entropy. A smooth universe is the exception, not the rule. If the initial condition was chosen at random from all possibilities, the probability of selecting such an ordered state would be vanishingly small. The numbers become absurd long before one reaches the full scale of the problem. For the universe to start in a low entropy configuration by chance is so improbable that it demands explanation. Merely stating that it happened this way does not satisfy the scientific instinct to seek deeper reasons. This is where the second path enters. Perhaps the universe did not begin in a low entropy state by accident. Perhaps something about the laws of physics requires such a beginning. Some researchers have suggested that the universe emerges from a quantum state that naturally minimizes gravitational degrees of freedom. Others propose that the universe is the optimal solution to some informational principle, such as maximizing the number of possible future histories. Still, others argue that the Big Bang is not a starting point at all, but a transition from an earlier phase, one that uniquely restricts the entropy of the newborn cosmos. One proposed idea is that the universe began in a simple quantum configuration because simple states are more fundamental than complex ones. In this view, the laws of quantum gravity might only allow smooth initial geometries. Any attempt to create a more complicated beginning would be unstable or prohibited. Another idea suggests that entropy as we define it is not meaningful near the Big Bang. Before space-time fully crystallized into classical geometry, concepts like gravitational entropy may not apply. Instead, the universe might have emerged from a pre-geometric phase with no concept of entropy at all, and the low-entropy beginning may reflect the simplest state allowed in that phase. A different line of thought stems from the holographic principle. If the universe is fundamentally an information storing system, then the initial state may be determined by informational constraints. For example, the early universe could have been the smallest possible state that still allowed the formation of observers or the emergence of complex structures. In this view, The universe began simple, not because of chance, but because complexity requires simplicity at its root. You cannot build a vast library without first having a blank page. You cannot create intricate entanglement patterns without first establishing a smooth fabric of correlations. Simplicity may be the seed that all complexity grows from. Another striking possibility is that entropy increases because of fundamental principles tied to information theory. John Wheeler famously expressed the idea that reality arises from information, a concept summarized as it from bit. According to this viewpoint, the universe is not made from matter, but from bits of information. If so, entropy might grow because the universe is performing a computation, expanding its informational content as it evolves. Each moment in time would correspond to the processing of information. The arrow of time would then reflect the one-way flow of computation. The universe would be a cosmic computer whose memory space increases as the cosmic volume increases. In this computational picture, the low-entropy beginning may reflect the initial condition of a computation, a starting state from which all later steps must follow. When a computation begins, its memory is blank or nearly blank. As it runs, it fills with information. This would mirror the universe's behavior. It began simple. It became increasingly entangled and structured. Its entropy grew. Eventually, like a computation approaching the limit of its memory, the universe may approach a final state dominated by horizons and thermal radiation. Entropy would reach an enormous value, but not an infinite one, defined by the informational capacity of space-time itself. This view does not compete with physics, it extends it. The laws of gravity and quantum mechanics are then seen as the rules governing how information evolves. The geometry of space-time becomes the architecture of the computation. Entropy measures how much information is inaccessible or dispersed. Horizons represent limits on what can be known. The universe becomes a story written in bits rather than particles. If this perspective is correct, then the growth of entropy is not merely a consequence of initial conditions. It is the expression of a deeper rule. The universe is compelled to move towards states of greater informational richness. The low-entropy beginning is not an arbitrary choice, but a necessary blank slate. It is the simplest state from which computation can begin. Yet even if such principles exist, we must confront the fact that we do not yet know them in detail. We do not know whether the universe prefers simple beginnings because of quantum gravity, holography, or computational law. We do not know whether the low-entropy beginning was selected, imposed, or inevitable. What we do know is that the universe behaves as though it began in a highly ordered configuration, and that its evolution has followed a path of increasing informational complexity ever since. Perhaps the resolution lies in a synthesis. Initial conditions and fundamental laws may not be separate explanations. They may be two sides of the same coin. The initial condition might appear special when viewed from classical physics, but natural when viewed from a deeper informational perspective. The laws we observe may arise from the universe's commitment to maximize possibilities over time. The arrow of entropy might reflect a fundamental preference for growth in information content, while the low-entropy beginning might reflect the simplest instantiation of that preference. In this sense, the universe may be a system that tends toward more because it began as little as possible. Simplicity was the seed. Complexity was the outcome. The question is not why the universe grows more complex, but why it began so simple. And the answer may lie in laws we have not yet fully uncovered. Laws that tie together quantum theory, gravity, and information in a unified framework. In the final chapter, we will gather all these strands into a single narrative. We will see how entropy gives rise to gravity, how entanglement gives rise to entropy, how expansion gives rise to information, and how the low-entropy beginning sets the entire process in motion. And ultimately, we will confront the deepest question of all. If entropy creates gravity, and if entropy itself arises from information, What created the information that allowed the universe to exist in the first place? Across the long arc of cosmic history, entropy rises with unwavering consistency. Stars ignite and burn their nuclear fuel into light and heat. Galaxies swirl into elegant spirals, only to dissolve over eons into diffuse halos. Black holes swallow matter and grow into monuments of hidden information. Even the expansion of the universe itself carries entropy outward, stretching horizons and hiding more and more of the quantum correlations that once bound the cosmos into a smaller whole. Everywhere we look, entropy is not merely increasing, it is expressing itself as the driving force behind cosmic evolution. But if gravity emerges from entropy, and if entropy emerges from information, then we must follow the chain one step further. What created the information in the first place? What was the first cause of entropy? To answer this, we must gather the threads that have unfolded across every chapter. Gravity, which once seemed fundamental, now appears to be a large-scale phenomenon rooted in the statistical behavior of microscopic degrees of freedom. Space-time itself, which once seemed smooth and absolute, now appears to be an emergent fabric woven from quantum entanglement. Entropy, which once seemed like disorder, now appears as a measure of possibility, of missing information, of inaccessible correlations. And information, which once seemed like an abstract tool for describing systems, now appears to be the very substance from which reality is built. The first cause of entropy is not a single event. It is the emergence of information itself. Before the universe expanded, before matter cooled, before inflation smoothed space-time, the universe existed as a quantum state containing correlations that could not be fully observed within any single region. These correlations created entanglement entropy, even in the simplest possible vacuum. When space-time came into being, these correlations were stretched and divided. The inaccessibility of the full quantum state created the first rise in entropy. Even a perfectly uniform universe is full of entanglement at the quantum level. The moment that space-time provided separate regions, each with its own future path, entropy existed as the measure of what no observer could fully know. Inflation amplified this effect. It took microscopic fluctuations and magnified them across cosmic distances. It stretched entanglement so far that regions that were once close became forever separated by horizons. When inflation ended, the universe reheated into a hot plasma, but the underlying geometry retained the smoothness that inflation imposed. From this smooth beginning, gravitational entropy began its long ascent. The universe had been given a blank canvas with faint quantum ripples drawn across it. These ripples became the seeds of galaxies, and those galaxies became the laboratories in which gravitational collapse produced vast amounts of entropy. Inflation did not create entropy directly. It created the conditions that allowed entropy to grow. The low-entropy beginning is therefore not the absence of information. It is the presence of limited gravitational information. The gravitational field had almost no freedom to vary. The matter distribution was smooth. The curvature of space-time was minimal. These constraints meant that the gravitational microstates were few. The universe began in a nearly pure state with respect to its geometry. As time passed, every deviation from that smoothness increased the number of possible gravitational configurations. The collapse of matter into stars increased entropy. The formation of galaxies increased entropy. The birth of black holes increased entropy dramatically. All of these processes represented the unlocking of gravitational degrees of freedom that had been restricted at the beginning. So what was the first cause of entropy? One answer is that entropy came from the moment the universe allowed separate regions to exist. As soon as there is a boundary, there is information that becomes inaccessible. Entanglement ensures that the whole contains more information than any part can know. When the universe expanded, it created more parts. That alone increased entropy. The moment space grew, possibilities multiplied. The structure of quantum theory guarantees that vacuum fluctuations carry correlations, and the structure of spacetime guarantees that horizons hide those correlations. Entropy is therefore a natural outcome of quantum mechanics combined with cosmic expansion. But there is another answer, deeper still. The first cause of entropy may lie in the choice of the universe to begin simple. Simplicity is not emptiness. It is the seed of complexity. A simple quantum state has little structure, which allows structure to grow. A uniform spacetime has little gravitational entropy, which allows gravitational entropy to rise. A low-entropy beginning is not a flaw in nature, but a requirement for the universe to evolve. If the universe had begun in a high-entropy state, nothing would change. Nothing would collapse. Nothing would ignite. Nothing would develop. No arrow of time would exist. The universe would be static, uninteresting, and devoid of structure. For a universe to tell a story, it must begin in a state that allows that story to unfold. In this sense, the first cause of entropy is the same as the first cause of time, structure, and complexity. It is the selection of initial conditions that unlock evolution. But was this selection imposed by law, or was it truly an initial condition without explanation? That remains unknown. It is possible that the laws of quantum gravity require the universe to begin in a minimal entropy state. It is possible that the universe is the simplest solution to a deeper informational constraint. It is possible that time itself emerges only when the universe occupies a certain kind of state, and that the low-entropy beginning was the gateway through which time could flow. Another possibility is that entropy arises from a fundamental tendency toward increasing informational capacity. The universe may prefer states where more microstates become accessible over time. Expansion, entanglement, gravitational collapse, and horizon formation are all processes that increase the number of possible configurations the universe can contain. Perhaps this tendency is not a consequence of initial conditions, but a reflection of the mathematical structure of quantum fields in curved spacetime. Perhaps the universe grows because growing creates more possibilities, and entropy is the measure of that growth. Yet even if such a principle exists, we face one final question. Why is there anything at all? Why is there a quantum field, a spacetime, an entanglement structure, a set of laws that allow entropy to exist? Why did the universe choose to become more than nothing? This is not a question physics can fully answer, but it can offer a perspective. The universe began in a state of extraordinary order, not to maintain order, but to unleash the potential for disorder, not to remain static, but to move, not to remain simple, but to grow into complexity. The low-entropy beginning was not an accident. It was an origin point. The first cause of entropy was the first expression of possibility. When the universe emerged, it contained the capacity for countless futures. Entropy is the unfolding of that possibility. Gravity emerges from entropy. Entropy emerges from information. Information emerges from the quantum structure of reality. And that structure appears the moment the universe becomes real enough to hold relationships, correlations, and patterns that can evolve. In this way, the beginning of the universe was the beginning of information. The beginning of information was the beginning of entropy. And the beginning of entropy was the beginning of gravity, time, complexity, and every story that followed. The universe did not begin with a force. It began with the possibility of difference. It began with a state that could change. It began with a quiet pulse of information that would expand into everything we see. And so we arrive at a final thought. Gravity may rise from entropy. Entropy may rise from information. Q and information may rise from the moment the universe chose to become more than nothing.